Okay, thank you. I'm just going to take a couple of minutes to give you an overview of quantum and why we're so excited, and then I'm going to let most of the time happen to the panel to talk about what they're doing. So we at IBM are building quantum computers, and we actually believe that in the next couple of years we'll have machines that will be able to do things we cannot do on classical computers. We call this quantum advantage. We'll do things either cheaper, faster, or more cost-effective than can run on classical computers alone. Many people start and think that quantum is the next technology. And I like to remind people, actually, quantum computing is the second quantum revolution in the history, okay? So what is the first? Well, the first happened about 100 years ago. Actually, this year is the 100th year of quantum mechanics. And what scientists realized is that nature actually is discrete or comes in quanta. And this has actually resulted in huge impact, right? You take it from lasers to MRI, solar cells, LEDs, atomic clocks, even the transistor. So to put an estimate on how much money quantum has produced, how much value, I actually think it's hard to do, okay? I would also say in this first revolution, it was even fundamental. Those that know natural science know before the first quantum revolution, people viewed chemistry as the fundamental and that physics was about emergent. This flipped it all around and brought all the natural sciences together. So what is in this second revolution? It's actually realizing that nature tells us something so fundamental that nature computes beyond simple addition, okay? In fact, it's bringing computer science and the physical sciences together to get at the fundamental limits of computing. I think you can think of it as quantum mechanics is the operating system of the universe. And what does this do? It actually allows us to solve new problems that were actually intractable on standard classical computers. I'm not going to go into deep technical of them. At the highest level, what quantum allows you to do, quantum computers, it allows you to model systems like model spins, atoms, quarks, electrons. This allows you to model with more accuracy and either get better estimates of chemical problems, material problems, or things like this. And this can result either in making better fertilizer, it can be stronger material that can be lighter, it could be new classes of drugs, and many more. The second is many problems that we counter, actually, when we represent them on a classical computer, they explode. Quantum gives you a way to look at, I call it hidden patterns in structured problems. And the most famous of this is breaking cryptography, breaking RSA. But more importantly, you can imagine, can you find patterns in either financial, can you model risk, can you do optimization problems and things like this. So from those two lenses, you can think of quantum is it gives you a better way to model nature because you're actually modeling with the calculations that nature has. And it gives you a way to model problems that are just ridiculously, they blow up on a classical computer. BCG, and they'll say more about this on the panel, have actually looked at these computational problems and estimated that if I can solve computational problems in machine learning, chemistry, optimization, that it will have over $500 billion of value created when the technology reaches tech maturity. Modeling computational chemistry will have a large positive impact in materials, energy, health, and life science. Modeling optimization risk will have a large impact in finance and insurance. So there is a large value, but how do we actually realize this value? Well, there are two things. We need, first, to have quantum computers. We need to have a platform where quantum calculations can run that are beyond what can run on classical computers. Second, we need a very large network of academic researchers, enterprises that are committed to understanding these problems. So I want to zoom in a little. Sorry. At IBM, we have actually deployed now over 75 quantum computers, and we have operating today 13 quantum computers at what we call the utility scale. This is beyond 100 qubits, where you can no longer simulate it with our classical computing. These are either in our data center in Poughkeepsie, in our data center in Europe or various different client locations in the world. For instance, I show one in Japan here, one in RPI University in New York, and one in Cleveland Clinic and in Cleveland, Ohio. If you zoom into the quantum computer, even though there's a lot of noise about quantum computing, at its heart is a QPU. At the lowest level, there are only two fundamental things that matter. How many qubits can you encode the problem in, and how many operations can you do? The number of operations you can do is basically 1 over the quality. So imagine you got this two-dimensional plot, and I've shown all the sampling of all the quantum computers there are on the market today. I put this dotted line, which I call the utility line. This is the line you need to be beyond. Otherwise, those quantum computers can be simulated with classical computers. And today, there's only two companies, here shown, IBM and Google, that have got beyond that utility. And so think of that as the lowest level. The second is if you want to, and this is where the panel get into, if you really want to build applications, useful workloads, you need to make sure that the problems that execute on the quantum computers run fast. Superconducting qubits versus ion technology is about 400 times faster to 2,000 times faster. And if you do simple calculations with pricing, it can be up to 70,000 times cheaper. Since we broke this utility line in 2023, we've actually seen this eruption of scientific papers. If we total all the papers since we put the first quantum computer on the cloud, we have over 3,000. But in the last year, you've seen about 25 papers by researchers doing algorithms, last year and a half, at this utility scale. So there's this change that has happened. So as we go one level down, we at IBM, we're building a compiler. That compiler we've chosen to be open source. We want that compiler so that various different software verticals can be built on it. Qiskit is the most performant compiler. It's preferred by more than 70% of the developers. It has many different projects that depend on it, and it's about 13 times faster than any of the competitors. Second, we want to basically get an environment where we can integrate classical and quantum computation together. And this is the Qiskit runtime, as well as Qiskit serverless, where we've shown that we can actually start to experiment mixing classical and quantum computing together. So coming back to my other point, we need an enterprise. So what we set out in 2017 was to create the IBM Quantum Network. I'm very proud of all the hard work the team has done. Today, we have over 50 industry members, over 55 commercial partners that include startups that are committed to starting to work out applications of quantum computing, over 170 research institutes doing algorithms, and over 6,000 users using it. So you can see that there's this vibrant community. If you zoom in just on the application partners, and many on the panel that will come up will go into the details of what they're doing, they are at a high level are starting to work out how we abstract quantum computing and build algorithms. Last year, to put this all together, we created what we call the Qiskit function catalog, where we could start to bring to this set of users a library of different applications, either applications at the lowest level, which abstract the noise, we call these circuits, or at the next level, application functions that start to work on how quantum computing will matter for those problems I talked about at the start, either in optimization, chemistry, machine learning. And what I see this as a way that we can start to bring both the hardware and the software of quantum computing to the users, to the enterprises that want to start using it. And putting this all together, I feel confident that in the next couple of years, as long as we work together as a community of hardware providers, software, HPC, as well as algorithm researchers, that we can get to a point where quantum computing is doing something that we call in the field quantum advantage. That is where we're doing something that's either cheaper, faster, or more cost-effective. So please welcome the panel. Emily is going to come to the stage and introduce. She partners with me and runs IBM Ventures. But I hope you see this high level that we're at this point, a disruptive change, where quantum is now moving from just hardware to actually algorithms and applications. Thanks.
Awesome, Jay. Thank you. Perfect. Jay, thank you. And thank you for the fantastic insights into the state of quantum, IBM's capabilities. in the ecosystem that we're building. It's no doubt now that quantum is no longer a research project. It's real and it's evolving quickly, right? Quantum advantage is around the corner. And the economic opportunities are tremendous. We're at the brink of solving computational problems we never thought possible before, as Jay just talked about. That is why IBM Ventures specifically is so excited about investing in quantum startups to help drive thought leadership and enhance the ecosystem. The groundbreaking advances are not just going to come from hardware, right? They're going to come from inventors that are bringing applications, they're developing algorithms, whether it be for optimization, material sciences, chemistry, orchestration, right, and so much more. We're going to hear about that with some of our startups we're going to bring up stage here. But at IBM, right, we are increasing the capital that we are deploying. We're expanding those partnerships, and we're helping those founders build great, amazing companies. We have incredible scientists like Jay, right? And therefore, we offer more than just capital, right? We believe in our capital plus model, and we'll talk a little bit more about that, which emphasizes our thematic approach. And as a strategic investor, we are committed to sharing expertise, providing mentorship, differentiated access, and collaborating to better serve all of our clients. And in return, the startups, and they'll share some of this, they drive innovation, they fuel our strategy, and they provide market insights. And of course, they offer great returns. As investors, that's important as well. But one of IBM's key strategies is to build an ecosystem, as Jay talked about, right? And we're doing exactly that with quantum. We have the largest network of quantum startups with over 45 members. And that is why I'm thrilled to welcome 4 of those partners to the stage. So I'm going to ask them to come up. Tenon Yang, come on up. And he's the co-founder and CEO of QNASYS. Michael here, I'm going to sit here, sorry. Michael Hush, who is the Chief Science Officer at Q Control. Yes, yay. Roman Orris, Chief Strategy Officer at Multiverse. And Matt Langione, who is the Managing Director and Partner at Boston Consulting Group. Matt is also the Global Head of Quantum for BCG. Excellent. Thank you, everyone. Huzzah. Okay. Good job. Okay, excellent. So,
It's okay.
first of all, thank you guys for being here. And Matt, I want to start with you, right? As we saw from Jay, there's an updated forecast that BCG just released, all about the quantum market, right? Based upon the work that you're doing, help us better understand the landscape, help us understand how you made that forecast, and what does it mean for the industry?
Well, let me just start by saying that, first of all, thanks for having me.
Of course.
And then, really, we think that quantum computing has the potential to be not one of the most transformative technologies of the next 10 years, but of the 21st century, with use cases that will dramatically impact the way that we live. Think about materials design and the potential to discover, a high absorption solar panel that could, power your entire house. It could be flexible. It could be the size of a credit card. Think about drug discovery to characterize and cure diseases that have plagued humanity for millennia. Think about the ability to address growing challenges like transaction fraud, identity theft. That's the power of quantum computing. And that's what leads us to believe that there's about $450 to $850 billion at maturity of value creation for end users. And we think that that end user value creation will lead to about $100 to $200 billion market for providers of the technology. So it's a very investable technology, to your point, Emily. This is a forecast that we've developed over about 7 years. I mean, of course, we've updated it regularly throughout. But it's based on a couple things. The first and most important is feedback from end users in industries. Think about chemists that are working on drug discovery, about the problems that they're facing in their workflows today. Those are problems that simply must be solved to unlock value. Now, whether that value will be unlocked with a quantum computer or another technology is the second part of the exercise. So once we understand the sort of trapped value or the opportunity cost that's out there in the industry, in the different verticals, we then undergo a process of analyzing the whole workflow to determine where problems will be uniquely addressed by quantum computers. In other words, where when you think about the rising tide of machine learning capabilities, there's a remainder. And that remainder is, in many cases, what we think quantum computing can address.
No, this is amazing. And I think you've pointed out so many of the important things. And I want to turn to some of our founders here, right, and hear what they're up to specifically as they're driving that industry. So, Michael, I want to start with you. Tell us about Q Control. I'm particularly interested in everything you're doing around the optimization solver.
Yes. So thanks for the opportunity to talk to you about quantum computing as well. So we've been working in the quantum computing space for 6 years now. We're Australia's first venture capital funded quantum computing and now quantum sensing company. And so what we do is we make quantum computing easier to use, whether it's teaching you how to use a quantum computer or making it more applicable to the problems you care about. So we both boost the performance of the devices that are available today, and we translate them to problems that your company faces. So we've been going at this for a while, for 6 years, and we've been in a great, I think we're in one of the earliest startup partnerships with IBM. So we've been working closely with IBM over this entire period. And we've been really seeing the improvements in the quality of the devices coming from IBM. So there really has been a significant change from when we first started. The size and scale of these devices were small but interesting and new. And now we're at this utility scale where if I use one of these devices from IBM available today, I can solve problems that are impossible, or what would be virtually impossible on a regular computer. The question at the moment just is, how useful is that? So we've been really focusing on figuring out where is that first opportunity? Where is going to be this like confluence, so to speak, of both just the right type of application of a quantum computer with the right kind of capital that's able to be invested with the right kind of timing, so it's like in the customer's hand as fast as possible. And so we've found that optimization problems in logistics and in transport have become like a very clear possibility for quantum computers to make a difference. We've worked with the UK government and the Department of Transportation, worked with New South Wales as well, in Australia, the New South Wales Department of Transport as well. And what we've looked at is we've examined the kind of transportation problems they have, whether it's getting people from A to B quicker or making their entire network more efficient. And what we've found is that there really are significant gaps in the efficiency and the ability of the current optimization techniques that are available to them to solve the problems they're trying to solve. And that results in dollars. So there is sometimes millions up to billions of dollars, depending on the size of the problem, just sitting on the table ready to be pounced on if we can come up with a solution that can solve it. And what we've found is that quantum computers are a really exceptional possibility. We've seen them working extremely well up to the largest ever optimization problem ever solved on a quantum computer was performed by us. And we're seeing a lot of great green flags that quantum computers are doing something special. They're searching in just the right way to find those solutions that wouldn't normally be possible with a classical computer. So we're going to eventually find out for sure whether or not a quantum computer is going to be that differentiator once the devices just get a little bit better. But we're talking now 2 to 3 years. It's just around the corner. And the only way to make progress on this topic is by using real devices at the utility scale, like at IBM.
Oh, well, there are a few things you talked about that I want to come back to, but I want to hear, Roman, from you. I want you to tell us a little bit of how you're bringing quantum into ML workflows, particularly. My first patent is in ML, so I'm very intrigued by this topic.
Yeah, excellent. So thanks a lot, Emily. So it's really a great pleasure to be here. So you know, at Multiverse, we do software for quantum computers. Okay, we focus, and in particular, we focus on building software that is useful for different industrial applications. Okay, and through this journey that we have been doing at Multiverse during the last 5 or 6 years, one of the things that was very clear for us is that obviously we need to be able to work hand in hand together with the people that are building the hardware, okay, to provide useful solutions for all the possible industry verticals. So essentially, one of these solutions is what we are deploying at IBM, which are quantum machine learning solutions for industry. In the way we are working in such a way in this workflow, so that we are trying to make the solution easy for different users, okay, and it's based on essentially it's a layer of quantum computing, okay, that is able to solve complex machine learning problems. So in the same way, instead of running a neural network, let's say, for building predictions or for doing regressions and so on, we have our own quantum machine learning algorithm for doing that. And the workflow is built in such a way that the user, at the end of the day, doesn't need to know anything about quantum, okay? Because something that is very important is that the final user, and I think this is very important, the final user doesn't need to be a quantum scientist, okay? This is something that we should have very clear in mind with the guys that are building the applications, because if we want to scale up this technology, everybody is going to be able to use this, okay? So in the end, what we built was a layer for using the IBM machine to solve complex problems in machine learning in such a way that, essentially anybody could use it.
That's perfect. Thank you. And then, Tenon, tell us a little bit about Qunasys, particularly around the algorithm development. I do feel like that's going to be the future as we build on hardware. So tell us a little bit about what you're up to there.
Yeah, thank you. Thank you for inviting me. I'm Tenin from Qunasys, and we are a Japanese quantum software startup and also building the quantum algorithms. So a lot of common misunderstandings, like that people will think, like if we have quantum computer itself, it can calculate exponentially fast, but that's actually not the case. We need the clever algorithms that use the best out of this quantum computer. And kind of what Qunasys is doing is like the building the powerful algorithms, and especially we are focusing on chemistry, like the material simulations. So kind of some example is like the Qunasys developing the algorithms, and kind of the old days, there's one algorithm called VQE, but we find out that it's kind of too costly to run on real devices, and kind of IBM has the estimate, like if you compared to supercomputer, if you want to run a big molecules, it will take like 2 million years to just calculate on quantum computer, even in quantum computer. And kind of we developed some algorithms, like more cleverly use supercomputer, and then kind of and build algorithms called QSCI, and kind of that IBM have demonstrated that running on quantum computer, and kind of calculation will be just in several hours. And kind of the accuracy needed for chemical calculation is not enough. So kind of there's a lot of room for improvement, but kind of that is kind of basically what we are doing. And kind of but kind of algorithm development itself, there's a lot of university developed that, and a lot of startups doing that, but our uniqueness is like more collaboration with end users. So for example, like we are having the partnership with like Toyota Motors, like they are interested in like the building the battery, etc. So kind of they need more precise calculations, and kind of for that use cases, we for the best of our knowledge, like we do resource estimations, what kind of quantum computer it will need it, and when we have that, what kind of speed calculation will be. Kind of we do a lot of that estimation with them, but kind of unfortunately we see a lot of bottleneck of that. So kind of how to overcome that, that is basically what we are doing.
Awesome, thank you. I want to dive into the development of the ecosystem because we know it's going to be really important as we advance quantum. So Matt, I want to turn it back over to you. I want, if you can, tell us a little bit about the application ecosystem. Tell us a little bit about how it's being captured in the quantum market, and where do you think it's going in the future?
Well, I'll start to talk about the future by way of the past.
Perfect. I love that.
When you think about how the great watershed moments in the development of applications on traditional classical computers, you think about things like the IBM Harvard Mark I, which was used to do the atomic simulations. You think about UNIVAC, which was Remington Rand, and wound up doing a lot of calculations, actuarial calculations and things like this. And in no case that you can point to in history is it a story about a go-it-alone tech provider that solves a full stack problem and delivers it to a client. Always it's the case that there's an ecosystem around it. In those two cases that I just gave you, there was some government investment. There was, of course, technology provider IBM in the first case, Remington Rand in the second. And then there were end users that would come in and effectively dictate with their data what they needed from a solution algorithm perspective. And of course, that worked at a small scale. What I think is different this time is that now, in classical computing, we have a mature, abstracted software ecosystem and expectations from end users. And that's where I think that what IBM's doing by making its platform open, and what Michael Roman and Tenen's companies are doing, which is building upon that open platform, is the connective enabling tissue that's necessary to really bridge what can be a pretty complicated gap from quantum physics to business applications.
Yeah, and I think open is so important that we emphasize here because you can't have innovation without open.
No.
Right? And so that's why IBM that is our key strategy, and it's been our strategy for quite some time. I want to talk about users, right? And so, Tenen, I'm going to turn it over to you first. Then Michael, I'm going to come to you. Tenen, who are your target users? Are they material scientists? Are they changing as the market evolves, as we just heard from Matt? Tell us a little bit about that.
Yeah, so kind of we are targeting mostly the chemistry company in Japan, and kind of what we find out is like kind of what we have is like we have some community called Q Park, and kind of in that community we invite like 50 or more like industry company, and mostly chemistry company, but some like Panasonic, like they're more not just develop material but more building devices. But kind of what we are doing there is like kind of start with offer. So kind of a lot of users right now, they don't understand what is quantum computer, why these devices can do the chemistry calculation, how these devices can benefit from them. So kind of we started with that level. So kind of offer them a training and kind of offer our product, and kind of we together just let them open the product to them and let them test use cases. And kind of, and kind of that level is kind of, I'll say we kind of leverage the user level, but kind of currently right now it's like they understand the technology and they see the bottleneck of this technology, and kind of I see in company like shifting, okay, with this bottleneck, how can we overcome? So kind of they're interested in more deep research with us. So kind of I see in that kind of shift right now.
Perfect. And then Michael, I want to go over to you. I've got two questions for you. The first question I want to ask, and then I'm going to ask a follow-up, is what are the benefits you're seeing from application services? And then I want to get to talking a little bit about your user base as well.
Yeah. So I guess we at Q Control, in terms of application services, what we do is we provide infrastructure software. So we sit between any user, actually, whether you're another quantum computing company, potentially, someone else developing software, and we boost the performance of that quantum computer with our control technology. So that's one part where it really just emphasizing the opportunity by having a full ecosystem is that you can have many layers sitting between the hardware and the actual end user, where you've got a variety of providers who can really get you the best you can from that hardware at the most affordable price and the quickest. So in terms of that's how we often work with other companies, is we're happy just to sit as a middleware layer who just makes sure that you get the right results you want to get faster. But then we also do a lot of work meeting directly with customers, trying to understand their needs. We work with a lot of different commercial partners like SoftBank, to a lot of government-related customers like the Australian Defence Force and the MOD in the UK. Yeah.
Awesome. And Roman, tell us about partnerships, right? Because one of the key things for IBM is when we are working with our startups, we want to understand their roadmaps, we want to understand their challenges, their successes, right? How are you building partnerships? Because we know that being successful in building the ecosystem, partnerships are a huge aspect of it.
Yeah, so for us, so that's actually a very good question. So since we are a software company, obviously we need partnerships to grow, right? And in particular to scale up. We are building lots of very useful software solutions for different industries and so on. But first, since we are a software company, we obviously need to partner with the hardware companies, because without the hardware, we cannot run the software, okay? On the other hand...
A perfect marriage here, I think.
Exactly, and also the hardware companies, if they don't have the software, they can also not run anything useful on their hardware, no? So that's actually quite a natural partnership. So for us, it's natural to partner with the hardware people like IBM, no? And also what is very important for us is to look for partners that can help us actually to scale up our solutions. Because, we can do many things on our own, but at the end of the day, we want to reach a global market, okay? We want to understand, we want to reach more clients, all right? We want to refine and fine-tune our solutions, and this is something that we value a lot in our partners. Yeah.
Yeah, I think that's great, and we work incredibly closely, of course, with our startups, right? And the reason I love the partnership so much with IBM, research between IBM Ventures, right, is because we both are at the forefront of innovation, right, which I think is so important. Michael, I want to put you on the spot here and ask you a very IBM-y question, if that's okay. Yeah. And that's all around how has IBM Quantum Computers allowed you to do the largest optimization demonstrations to date? Because that's a huge feat, right? Yeah. So tell us a little bit about that.
We've been very proud of that. So we don't just use IBM devices. We use all devices that are available to us. But we've definitely had like a very, very great relationship with IBM from day one. And I think it really actually speaks to the great relationship we've had, the effort that's been put in from IBM, and the work we've done together. That we've really seen an incredibly massive advancement in the technology. So IBM's devices have got significantly better year on year on year. And what has really been a fundamental part of us putting together this big demonstration has been literally the improvements in the quality of the technology. Yep. And I really just want to emphasize that is critical. Like, a history of improvement is a very good sign if you're looking to figure out what partner you're going to be working with. Yes. So that's always been very close to our hearts, is that history we've had and that continual set of improvements we've seen. And then on top of that, we've been able to work with the devices for many years. So we've been working on these machines for 6 years. We've got a really good understanding of that technology. And so we were able to use that to do this demonstration at a scale that had never been achieved before. And it puts a gate-based quantum computer now in the lead, so to speak, on any kind of optimization problem. What was also important for us in that moment was just, first of all, once we built that technology, once we were able to demonstrate it for ourselves, the ecosystem that IBM provided then made it available to everyone else. Yeah. So that investment we've made and that partnership together not only benefits the products we're putting together, but also benefits everyone in the ecosystem, which they can then leverage. Yeah.
Yeah, and I think I would just pause there for a second, because one of the key things we're trying to do is build an ecosystem, right? Yeah. And build partnerships and be open, and so that we can all collaborate together. Switching gears just a little bit, Matt, I want to come back to you, right? What are the challenges and opportunities that you're seeing?
Well, I think, to answer that, I would say the folks to my left here are engaged in something extremely difficult. Yeah. If you think about classical computing and the way that software develops, it's with really test-driven engineering, right? There's a cycle, kind of a dev, test, debug cycle. It's not as though you go into kind of a lab or an ivory tower, come up with a software solution and just release it into the world, right? Yeah. It's very, very iterative. In my experience, which is limited and maybe not so successful in coding, it's sort of like 5% coding, 95% debugging, right? Yes. Now, it's been extremely challenging to leverage quantum hardware to do that test and debug. Yep. Because of just the maturity of the hardware. Now, IBM, I think, has been extremely exemplary in setting a roadmap early, probably at least 5 or 6 years ago, and with metronomic consistency hitting the milestones year after year. But I think only now, so we've talked about the challenges with algorithm development, only now do we stand at the precipice of, I think, the really, really critical period that leads to quantum advantage, where algorithms can be developed not just, kind of in a lab or not just in an ivory tower, but in a true traditional hardware-aware, test-driven engineering process that is typical of all of the best innovations that we've seen in software.
Yeah, no, that's great. And look, I think we've got startups in the room, we've got investors in the room, we've got engineers in the room. What advice are you giving them?
Well, so for startups, my view is that there's never been a more auspicious time to start a quantum software company.
Yep.
I think these folks have really endured through a difficult 5 years where they were doing things with just an extreme level of difficulty. I think that the next 5 years are, I think, just a little bit more auspicious. So that's what I would say. From an engineering perspective, my view is that I think that there may be a misconception that in order to add value to this quantum solution stack, you need to have a PhD in quantum physics. I think that, of course, it's helpful. And of course, PhDs in quantum physics are in short supply and very, very useful. But I think that, that what's really necessary is expertise in one of the critical domain areas where quantum computing is potentially potentially advantaged over classical computing. And some of those advantages, by the way, are exponential in nature, right? So the value creation is accordingly really, really high.
No, that's great. Roman, what type of investor are you looking for, and what advice do you have for startups?
Investors. So what do we look for in an investor? We look that they support our vision, actually. An investor is more than just the money. Obviously, the money is important, but I think it's as important as the money, or even more important in some cases, is that the investor is actually sharing your view of the game. Okay, they are able to support you in what you are trying to build. Okay, and the investor obviously they also bring a lot of networking connections, expertise, and so on that can help a lot in an infinite number of ways beyond the actual money. So for us, that's actually very important. And the investor actually is able to share our vision of what we are trying to do. Okay. Yeah.
Excellent. Michael, thoughts on that? Advice for some of the startups here, investors you're looking for?
Yeah, I think definitely on the startup side, I would say just talk to customers. I think that's something that is like someone with a technical background who comes into the space. You've got to start talking to customers as soon as possible. Often, most people in the field have a good idea about the technical work that needs to be done, but just really don't understand the impact it's going to have. So getting in contact. And then also getting onto real devices. That's the other big gap I see, is that quantum computing sometimes is taught in a very abstract way, but the reality is the devices are doing amazing things, and they do it in a very specific way, and the more you can understand, the more you can get out of them. I was also just going to highlight the other, you mentioned also like what are some of the problems that we're facing in the industry?
Please.
Yeah, I was just going to say, I think the thing that I want to see more of, and it was great to see on Jay's presentation today, this 2-year number. It's giving timing. So one of our biggest challenges, I think, when it comes to talking to customers and making them understand the opportunity, is there is a bit of an inconsistency within the quantum space at the moment about when we see quantum advantage actually occurring. And 2 to 3 years to me is an incredibly reasonable number, something that we can all hit. So that's what I would also be is
But that's why we're doubling down on our investment, because it's real. It's here,
real.
right?
Exactly.
And that's why we're so excited about it, right? And partnering with BCG to help us understand, okay, well, what does the industry look like, right? We know it intimately for startup, but we're excited about the advances because of where we're at and all the great stuff you guys are doing.
Yeah, 100%. And anyone who thinks otherwise needs to go and check the real devices and see how far they've come. That's what I would say. Yeah.
Totally.
Yeah.
Teddy, over to you. Advice for startups, looking for investors, what do you look for? Anything you want to add on challenges, opportunities that you see? Before I ask my last challenging question.
Yeah, maybe I will kind of go to the advice to the startup and kind of investors. And so kind of what we see is it will be like, I'll say, the interesting time from now. And especially what I'm interested in is error corrections. Like there's a certain technology that can kind of reduce the quantum computing error dramatically. And kind of that is kind of what this industry is kind of truly, hoping for, and kind of in that sense, it will be kind of easier that we do. Okay, if we with error-corrected devices, what application can we run in which time? That can be kind of really simulated right now. So kind of what we think is like as Michael pointed out, the roadmap will be quite important. And as an investment, okay, if we have these devices, what application can we run? That can be kind of, simulated right now. And kind of we are building technology to simulate that. So kind of to invest in quantum, to see current devices, maybe it doesn't it cannot do something industrial powerful right now, but in the future devices it can, and kind of that can be simulated right now. So kind of seeing the future of the roadmap, I think that's kind of the advice I would.
Perfect. Excellent. Matt, I'm going to put you on the spot. I'm really going to put you on the spot this time. What inning are we in quantum? If I'm going to use a baseball metaphor, I wish it was basketball, it's my favorite, but I'm going to use a baseball metaphor. Tell us what inning we're at.
Well, I think that, I mean, if you think about it, Jay pointed out a kind of 100-year history of quantum computing. There are other, landmarks that you could point to, like the early 80s, the MIT IBM conference. I think, the late 90s, the development and characterization of the superconducting qubit. My sense, when I like to think about things from a kind of value creation perspective, I think that we're kind of in the early innings still, really. I mean, I would say we're in inning, let's call it inning 3.
Okay.
Where this is now, I think, an engineering problem. I didn't think that 6 months ago, but Jay has convinced me that this is more than anything an engineering problem. And that's a really important distinction, because then you can draw a direct line from where we are to business impact. And now when that happens is a function of course, good engineering, capital, and some luck. And adoption as well. But I think that we're now, let's call it inning 3, where a lot of the fundamental science is in place. There's engineering that needs to happen, and very critically, there's enterprise adoption, I think, that needs to happen.
All right, I got my last question for you guys. One word to describe how you feel about quantum. Tenin, we're going to start with you. One word. Give it to us.
Yeah, so I will go with telescope.
Okay.
So kind of, I believe it's a tool. So it's not the ultimate goal is not building quantum computer, but rather use it to do a new scientific discovery. And that is what we are doing.
Yeah.
Roman?
Well, I'm going to be more optimistic.
Okay. Excellent.
I'm going to say rocketing.
Okay.
Rocketing, yeah.
Excellent. Michael?
I think honest still. It's like still a really honest industry, I find. So like,
Wait, tell us more about this.
I just mean that the.
Are we saying AI is not honest?
No. I'm not trying to do this like for other things. But given how big the opportunity, given it's a $500 billion opportunity, there's a remarkable amount of honesty between most companies about where the hardware is at and where the technology is at. And I would highlight again, it really is an engineering problem where everyone understands we're solving it all from different angles, but we're going to get there. So it really still feels like that, which is good. Yeah.
Matt?
I'm going to go with exponential.
Okay.
Because that's the critical advantage you're looking for in the solution stack. And also, I think that quantum will be exponential in its ability to accelerate the scientific discovery that we need to change and improve the world.
I love it. Well, first of all, thank you guys. This was incredible, an amazing discussion. And I'm going to pick a word. We had this debate, right, with the IBM team. I heard transformational, I heard dynamic, I heard all kinds of amazing words, right? But all of the things you guys said is exactly why we are so excited to continue partnering and investing with startups, focusing on quantum. We also focus on AI, a little plug for us there. But the companies that you see here today and the companies that are also in our ecosystem, right, they're building quantum of today that's going to be that next decade of computing. And it's really, really exciting. So thank you all. Appreciate it. So thanks, everyone.